All right. This is a bit of a speed run. Well, an introduction to logistic regression. And with not a ton of math notation, I just want to go over the ideas of logistic regression and kind of getting towards what it looks like to get under the hood without all the unnecessary complicated fluff. Okay. So, logistic regression is probably something you've heard of if you're clicking on the video. And to me, it felt pretty complicated until you kind of understand what the point of it is and why it's useful. So, logistic regression, despite its name, is just a tool in machine learning to, given some data as input, output a prediction. We'll talk about the data in a second, of true or false. You can think of it as 0 or 1 or hot dog or not hot dog, but it's a binary classifier is what it's called because it's just putting something in one bucket or the other. So with some probability, which we'll talk about in a second. So the what's the input? The input is just normal data. Talked about in the last video about linear regression. Normal data of let's see. Let's say now we changed the data from last video. So goals scored by Messi in a game. So 2, 0, 0, 1, 1. And then did they win or not? So 2 goals scored would be true, false, false, true, false. So this is maybe some data I've collected about Messi. And then for a new, so that was the data that I collected. And then for a new data point, 3, what is, basically, I want to know the answer there. I want to predict an answer there. And obviously you could have more things than goals. You could do assists. And then that would maybe make our predictions better. But that is basically the input. The input is some data, some labeled data with the actual outcome. And then we're going to have we're going to be able to make predictions if we input the goals scored. Okay, awesome. So what is actually going on here when I say we're going to predict a probability of a binary classifier? It's kind of confusing. So first of all, let's just go back to linear regression. And the idea with that is that you're fitting a line to data, you're have these data points, and then you're drawing a line that looks good in between them, and then so you can use that line just to make predictions. So if I want to make a prediction about this value, then I look and see what the corresponding y value is, and then this is my prediction. So linear regression is great. It's just finding the equation y equals mx plus b, and finding the best m and b to find the best line. And of course you can do that in higher dimensions, but it's all the same. Okay, so logistic regression starts with linear regression. The actual way of computing values for logistic regression, you do a linear regression first. So if you know linear regression, you already know the first step. Then the second step is called the sigmoid function, logistic function. They all have similar names, and understanding where that function comes from is a bit out of the scope of this video. But basically, you take the output of the linear regression. So let's call this Z. So z was the output of our line, and then we're going to take that output and put it into the sigmoid function. So it looks like this. And then you get a number in between 0 or 1. So you can see here, if our number was, let's say like 1, if z outputted 1, that's a bad example. If z outputted 3, we will get a number that looks like pretty close to 1, maybe like 0.9 or I don't know, something like that. And if we had a really low number like -3, we would get something more like 0.1. Great. So sigmoid function outputs a number between 0 and 1, which is perfect because then we know y equals sigmoid of mx plus b, or sigmoid of z, the same thing. And this outputs a number between 0 and 1. So we know y is a probability, a valid probability, which is really good because that is our expected output. Well, maybe not quite. We have one more step to do, which is basically convert y to the binary output. So basically it's just convention to say if y is greater than 0.5, so it's more than 50% likely, then we output true. If y is maybe 0.4 or less than 0.5, then we output false or 0 or something. And so that is how you go from the input to the output, predicting true or false. Okay, so let's go through that with a little bit more math. So basically what you want to do is you're trying to find what's the probability of this y ground truth, or this yeah, exactly, this y ground truth, which is a random variable. So yeah, I mean, like, that's basically the whole thing. And then we want to basically find how do we know? Okay, so let's go back to similar question as linear regression. How do we know that the m and b that we picked are good? How do we know they're any good? Well, last time with linear regression, we had this function that was the sum of squares. But we can't actually do something so nice because of the sigmoid function. So our new error function, or sum of squares function, is now called a loss function. And that looks like this. And I guess we'll work backwards to see where it comes from. Okay, so I guess you can predict that these are related. Okay, well, first, if we want to expand this anymore, we're going to have to know what this equals. And so this is the same thing as, sorry, okay, so this is a piecewise function so the ground truth can either be 0 or 1, right? So those are the two values that it takes on. And then it's just this sigmoid of mx plus b, or 1 minus. Okay, cool. So then we can replace this with, so this, oh God. Okay, so this is getting into the weeds of the math, but if you understand up until this point, you understand what's going on with logistic regression. So now we want to do the more complicated part of determining how good the m is and b is that we chose, and then finding ways to actually learn those parameters. Because last time we could just do least squares, which was kind of an easy shortcut, but actually this time we can't do that, which is super unfortunate. So we're going to have to do something called gradient descent, which is a whole nother adventure to go on. But for now, we're going to do some quick maths. Sheesh. Okay. Sorry, this is not written out very well. Okay. Great. So we want to maximize the likelihood of this data. But this is our loss function, which is great. So for our choice of M or B, we can use this to see how well we did. So how do we find the best M and B? Like I said, it's gradient descent. Okay, let's speed run gradient descent and see how well I understand it. Okay, so let's rewrite this loss function, or likelihood function in this case. And what likelihood are we talking about in this case? We're talking about the likelihood of all of these. So y ground truth refers to this column. And so we want to maximize the likelihood of that data existing given the choice of our parameters. So the choice of our parameters is kind of the input to the likelihood function. And so we want to maximize the likelihood function because maximizing the likelihood of the data sounds kind of good. Okay, so the likelihood equals, for all of our data points, right? So we have n data points. We're going to get into the math here. So sigmoid of mx plus b. So we did a little trick to turn it from a piecewise to a regular function. Hopefully that wasn't too confusing. And you can see why it still works. Okay, so here's our likelihood function. We want to have some sort of strategy to maximize it using like input. We want to input the best m and b to maximize this function. All right, so if you've done MLE before, then this looks fairly familiar. And the next step would be log likelihood. This turns into a sum of y ground truth log of sigma. All right, I'm just going to start writing z's for the mx plus b plus 1 minus y ground truth of 1 log 1 minus okie doke. Okay, so nothing changed there, just took the log of both sides to help us do some math easier. Okay, so here's the log likelihood function. So in calculus, obviously, if you want to max something or argmax something, you take the derivative and set it equal to 0. And we're going to do that to an extent, but unfortunately, if we try and set it equal to 0 and solve for m and b, it's not possible. So we need to have an iterative algorithm that we can continue